Hello everyone, I'm Simone Albanesi, a PhD student from the University of Turin. Today I will talk about gravitational waves from eccentric compact binaries. In particular, I will focus on the effective on-body approach in the extreme mass ratio limit. If you want to know more about this, you can consider this paper. Now here I've reported the typical evolution of a black hole binary with the spiral, then the two bodies plunge toward each other, they merge, and then finally with the ringdown. Here there is the corresponding gravitational wave, and this is computed under the hypothesis that the orbits are circular, and the reason for this assumption is that the emission of gravitational wave from the system causes the circularization of the orbits. So like numerical detect signals that arrive from circular binaries. But there are some cases when the eccentricity cannot be negliged. For example, in binaries that are perturbed by a third body, in dynamical captures, or in extreme mass ratio spirals. The latter are binary systems where a compact stellar object orbits around a supermassive black hole, and in these cases the orbits are non-circular and neither planar. These systems cannot be detected by Virgo, but will be detectable by LISA. So we want to solve the two-body problem in GR, so we have to solve the Einstein field equations, and we can adopt some approximations, and we can solve the analytical. So for example, we can expand these equations in the velocity, so assuming a small velocity, and we obtain the post-Newtonian theory, but we can adopt also other approximations, and we can find the post-Minkowskian or the gravitational self-force theory. If you want to solve these equations without approximation, we can consider the numerical relativity simulations, so we solve them numerically, but this is very technically difficult and you have to run them on supercomputers. Moreover, if one of the two bodies is much smaller than the other, these simulations are even more difficult, but in this case you can rely on the black hole perturbation theory. So you can linearize the Einstein field equations around a black hole solution and consider the small body as a perturbation. And in the most general case of a rotating black hole, you obtain the Tukowski equation. The Tukowski equation is much simpler to solve that the Einstein field equation is not simple, okay, but it's simpler. So if you want to describe the model analytically, we can consider the effective one-body model. The idea is to map the two-body problem in one body that moves in an effective metric. In this metric is a deformation of Schwarzschild or Kerr, and the parameter of this deformation is the symmetric mass ratio. If nu is equal to 0, we obtain the Schwarzschild or Kerr solution. This model is based on post-Newtonian theory, but it's very flexible. In fact, we can include also information from numerical relativity or gravitational self-force theory or other methods. This is very accurate for circular binaries, but now the challenge is to use this model also for non-circular binaries. In this talk, I will focus on the test mass limit, so I will consider eccentric quadrupolar orbits of a test particle in Kerr spacetime. Here there are the building blocks of the model. So the first one is the Hamiltonian, and if we are in the test particle limit, the Hamiltonian is simply the Kerr Hamiltonian. Here I've written for restricted to equatorial motion in this case, and this contains all the information on the geodesic. So if you solve the Hamiltonian equation with only the Hamiltonian, you get the geodesics. But we know that we have a gravitational wave emission, so we have to parameterize this effect in some way, and the non-conservative part of the dynamics are described by the radiation reaction force. In the quasi-circular case, we have only the angular component, and so with the Hamiltonian and radiation reaction, we can compute the dynamics. Here there are two examples, one for negative spin. Negative spin means that the orbital angular momentum is anti-aligned with the spin of the central black hole. Then from the dynamics, we can compute the waveform. In the OB model, the waveform are decomposed in multiples, and each multiple as a Newtonian contribution and some post-Newtonian factors. And here you can see two examples for the dynamics that I've shown before. But now let's move to the centric case. In Newtonian mechanics, it's easy to define the semilatus, rectum, and the eccentricity. They are two constants of motion, and they can be written in terms of the apastron and the periastron. In general relativity, we cannot define the eccentricity in a gauge invariant way, but in the OB model we can use these definitions that are the same in the Newtonian mechanics. The difference is that the apastron and the periastron are computed by solving the energy equation, setting the conjugate momentum of the radius equal to 0. So we have a definition of eccentricity and semilatus rectum, but now these quantities are no more constant of motion, clearly, because we have gravitational wave emissions. And let's see how to modify the model. So the Hamiltonian is already okay, contain all the necessary information because these are simply geodesics in Kerr space-time. But we have to modify the radiation reaction and the waveform. So first of all, we have to consider also the radial component of the radiation reaction force. This is a result from Bigin-Damour, and we have applied also up the approximate. The other two factors in the angular component and in the waveform are Newtonian non-circular corrections, and even if they are Newtonian, we can see here that they are good enough to describe the waveform. The black waveform is numerical, and the red one is the one computed with the OB model. We see that there is a good agreement. Clearly, it would be better to add terms beyond the Newtonian level, but this will be done in the future. So now we have the analytical model, and we want to test it. We want to see if this is reliable on all the parameter space. So we consider geodesic motion. We consider many cases with different eccentricity, different spins, and we compare the analytical results with the numerical results. Numerical results are obtained with Teo code, that is a code that solves in the time domain the Tokowski equation. We compare the waveform and the fluxes. Fluxes are very important because this comparison tells you how reliable is your prescription for the radiation reaction. I will not discuss this in this talk, but you can find analysis in this paper. Here I reported two examples. I've reported the dominant mode, the quadrupolar waveform, but clearly you can do these comparisons also for the other modes. And there is an example with moderate eccentricity, one example with higher eccentricity, and you can see that there is a very good agreement between analytical and numerical, both in the ambient and in the phase. Nonetheless, there are some cases, some extreme cases with high eccentricity, high spin, that have a less good agreement, and this is linked to the fact that the particle can get very close to that ring, so there are quasi-normal mode excitations, and you can see this in the waveform, and we get very high error in those cases. But these are extreme cases. In general, we have a good agreement between analytical and numerical. Let's say for moderate eccentricity and moderate spin, the agreement is very good. Now let's move to another topic. Let's discuss the waveform, but after the merger. So we have only one body that is excited, and we can describe it using the black-hole perturbation theory. We can solve the homogeneous Tokowski equation and find the quasi-normal mode that are the solution of this equation. The waveform will be a superposition of these modes, and these modes are damped oscillations because the frequencies are complex. But the point is, the coefficients of these superpositions are time dependent. So we have to take into account this effect, and one way of doing so is to factorize the fundamental quasi-normal mode and fit the remaining part of the signal on numerical data. So here there are two templates, amplitude template and phase template. There are many free parameters, but some of them can be constrained requiring the continuity between the waveform before and after the merger, so the continuity at merger. And the other parameters are obtained by fitting these templates on numerical data. So we do many fits. We fit the model for different values of the spin and the eccentricity, and we get some parameters in the parameter. We get some fit parameters in the parameter space, so we can do a global fit, and obtain an analytical model for the ringdown. So now we can match the solution that we have seen before for the spiral with the solution for the ringdown, and we'll do this using the quasi-circular corrections, the area of rectum, okay? And this is a way to smoothly attach the two solutions. And here there is an example, a non-spinning example with moderate eccentricity, initial eccentricity is 0.2, and we can see that the agreement is good both in the spiral, in the plunge, and in the ringdown, both for the amplitude in the phase and also for the frequency. This is the quadrupolar waveform, but clearly you can consider also the other modes. This is the model is reliable also for spinning binaries, and there is an example for spin 0.4. Finally, I just want to mention that the model can be used also for dynamical captures, and here there is an example. So to conclude, the OMB model is a promising analytical framework that we can use to describe memories, but we need to further improve the model. So first of all, we have to include correction, non-circular corrections beyond the Newtonian level, but terms at 2 post-Newtonian orders are already viable, so we can consider them, and we will consider them in the next future. We will also to consider the gravitational force effects that have to be included in the conservative part of the dynamics, and moreover, in the future, we have also to generalize the model for non-equatorial orbits. That's all. Thank you for your attention.